The network we saw in the previous example, in our motivating example, contained a resistor, inductor, and a capacitor. Okay, it was a what we call a RLC circuit. Okay, so the previous circuit was an RLC circuit. So what I'd like to do is do it one step at a time. Okay, let's do a simpler circuit, just the LC circuit. Okay, and that will itself give us a bunch of intuition. And then in the next sequence, I will introduce a resistor into the circuit. So let's start with a LC circuit of the following form. So let's say I have some input Vi of t. I have an inductor L, and I connect that to a capacitor C. And let us say that the capacitor has voltage V of t across it, and the current through the inductor and through the capacitor is I. Okay, so Vi of t is the input. I have the current I of t going through the inductor, and since it's a series circuit, the same current I of t will also flow through the capacitor. Okay, and the capacitor has the voltage V of t across it. Okay, and just remember, we will introduce R into the circuit in the next sequence, and here let's just look at this much simpler circuit. Okay, let me just write that down so you remember it. Alright, so I'm going to solve this circuit using the node method. Okay, so what I want you to understand is, going forward, it is all going to be about the node method, and once we write the equation that comes out of the node method, it will be complete math. Okay, so let's go ahead and write down the node method. And in order to do that, one of the first things that I have to do is pick a ground node, because I want to pick this as my ground node. And if I pick this as my ground node, then the node voltage here is going to be V. Okay, so let me go ahead and use the node method to solve this circuit. So moving on, so I show you the circuit here, and notice the current I of t flows through both the capacitor and the inductor because they're in series. The ground node here, and my node voltage is V. Alright, so recall the node method. Since I have a voltage source here, I already know the node voltage here, which is it is simply Vi. Okay, I've been careful in choosing my ground node to be one terminal of the voltage source, and so right away I have found the voltage at this node. So all I'm left with is one unknown node voltage here. And recall the node method? In the node method, all I have to do is I have to sum the currents going into the node with the unknown voltage, and either sum the currents as 0, or I can sum the currents leaving the node, and they will add up to 0. Okay, so I have to add up the currents into the node from the inductor and into the node from the capacitor. So let's do each of these things. Okay, so what is the current through the capacitor in terms of the node voltage? Well, that's pretty easy. The current through the capacitor I know is I of t, and that is simply given by C dV dt. Okay, V is the node voltage, and so the current through the capacitor is simply C dV dt. Okay, that's I of t because, you know, that's the current through the capacitor. I can do the same thing for the inductor. And so what is the current through the inductor in terms of the node voltages? Okay, so recall for a inductor, the voltage across an inductor is related to L di dt. Okay, so for an inductor, the current through the inductor is I, and if the current is I, then the voltage across the inductor is related to L di dt. So this is the V across inductor. So voltage across the inductor is L di dt. And in this case, what is that voltage? Well, that voltage is simply Vi minus V. Okay, so Vi minus V is the voltage across the inductor, and that is simply equal to L di dt. So now I'm ready to proceed with the node equation. Oh, but before I do that, let me just go ahead and express the inductor current not in its differentiated form, in this differential form, but in the use the integral form here. So I can go and integrate both sides with respect to t, and divide throughout by L. So if let's say I bring L to this side and then integrate it, what do I get? I get 1 by L. I integrate minus infinity to t Vi minus V dt, and that is equal to I. Okay, so it's a di dt up here, and by integrating both sides, I get the following equation. So right here, I have, this is I of t. So notice that the I of t flows through both the inductor and the capacitor, and so I can simply add them up, and they should sum to 0. So the I of t through the inductor must equal I of t through the capacitor. Okay, so in this particular situation, notice that I of t is entering node V, and here I of t is leaving node V. So I can write it as the inductor current minus the capacitor current is 0. Or I can simply equate the two, and I can write the expression like so. I can simply write them as 1 by L minus infinity to t Vi minus V dt equals C dV dt. Okay, pretty straightforward. Okay, so there I get my equation relating the node voltages and or rather node voltage V, and I have an equation that derived from the node equation. So let me get rid of the integral sign here and simplify it a little bit and differentiate throughout with respect to t. And what do I get? I get 1 by L Vi minus V equals C d squared V by dt squared.